First of all, I would like to say thank you for Keith and Fran for organizing this meeting, and I assume there are other people involved too. I really appreciate it, especially for Derek Sitters and Fran for arranging the bus from Edmonton to Grand Prairie. I think one of some of the best comfortable ride I ever had from Edmonton to the Grand Prairie. It was very comfortable, especially the bus has a V5. So I'm going to talk about today the monitoring tools that we've been doing the last 2 years, and this year is actually the final year we're going to do. We'd like to introduce the Jennifer Clash PhD students and my postdoc Jonathan Gill involved in this research. What we do, pheromones are really important sort of tools that we can use in pest management. These are the chemicals that are produced by insects and responded by the same individuals, both sexes in this case of mountain pine beetle. What we have, and the synthetic pheromones is being used actually since 1960s and 70s, even earlier in the agricultural system. They are really, really important tools for us. Unfortunately, there is uncertainties about the effectiveness to monitor beetle populations in this naive range, such as in Alberta and other novel habitats. That is really the focus of my talk today. Pheromones are used in multiple ways. Some ways, for example, they use attached to the traps and then to monitor the beetle populations, especially endemic levels. And in other cases, they attach on the trees and let's see the beetle respond to it. Really, in this case, for example, we're really faking the sort of artificial attacks and bringing invitation to the trees on here, come and see it. By this way, this allow us to detect their presence. They monitor the population fluctuations because beetle population they really fluctuates a lot in the landscape based on the spatial and temporal components. And this also allows us to concentrate the beetles into the baited trees. So this could be important if the beetle populations are reached at endemic level, they can be removed safely, and also prevent spread from a baited area. There are two objectives that we've been following. First is really improve the current available commercial lures to attract mountain pine beetle in the novel habitats. These commercial lures that developed from 60s, 80s, 70s, being tested in John Gordon's lab and may or may not be applicable here in Alberta. And when we were testing that, second is develop some sort of field protocol for deployment of these lures on trap trees to monitor and detect beetle population in novel habitats. First of all, I'm not really going to go in details. In 2014, we tested this experiment with the different pheromones, including incorporating some of the host chemicals in it, and we found that actually these are the chemicals we found that. I will go with that. These are the pheromones we tested. This is the result we found that after 1 year of experiments. Transverbenol, Exobrocomum, and terpinolene. This is the standard mountain pine beetle lure, and if we added the myrcene, actually we triple the number of beetles attracted to the traps. You know, the triple is a good number actually. You're increasing your risk. This could be very important, especially when detecting the beetles at the low densities. So our phase 2 conducted in 2015. We look at the developed field protocol for deployment of this new lure to monitor the detect beetle populations, where we were testing three things really: trap tree formation, density of trap trees, and density distance effect on beetle colonization. You may not know what they are, now I'm going to explain it here. This is very, very intensive work actually, I have to tell you. A lot of people involved in this. We have three types of formations: triangle, square, and rectangle. Basically, we put a bait on each corner of this shape. In this case, we have rectangle is 3 baits, square is 4 baits, and is a triangle. Here is the 4 baits. Doesn't look like triangle much, but it is. No, this is square, and this is the 6 bait triangle. So basically, 6 baits were baited along these shapes. What we did, this is a one formation. Each formation is repeated 3 times on the landscape in the same flat configuration. We also use the different distances, 1, 4, and 8 kilometers between each same type of configuration. For example, you can see here, this is the 1 kilometer configuration for triangle formation, and then this is the 4 by 4 meter configuration for the square formation, and this is the 8 kilometers among the rectangle formations. And each formation is repeated 3 times on the landscape, and we kept the minimum distance between each formation is about 10 kilometers. We end up baiting really 351 trees on the landscape. It was a massive undertaking in 2015. What we did is really, we look at these aspects, how the beetles colonize the trees. We calculated, quantified the low attacks versus mass attacks based on some published records. Basically, we look at the number of attacks between 1 and 2 meter portion of the tree stem and count the number of attacks based on the pitch tips. And we also have a mass attacks that the same thing. Based on these calculations, if attack rates below the 31.25 attacks per square meter of the stem, we call them as a low attacks. If it's more than that, it's mass attacks. Of course, in some categories, we have no attack. We also calculated the number of unbaited trees, spillover attack basically, around each baited tree, about between 15 meter in diameter area. That's a really, again, number of trees that we detected. This gives us a really good analysis of how the beetle attack the trees on the landscape and how they affected the trees adjacent to them. This is the area. This is about 16,000 square meter area, kilometer square meter area. Actually, all of these locations we have. I don't want to go into details. Again, these are the results. Well, we found that number of attacks on the baited trees range literally from 0 to 75. 75 is really indicating is a huge attack density within that 1 meter area. But we're really proud of it. We have about 91.3% of the baited trees receive at least 1 attack. It means that the baits that we use in our experiment, actually, in this assay, that really do a good job. I'm not sure what's the ratio for other trees, but this is, I believe, is significant. Now I'm going to show you the results in the same formation. First we look at the proportion of the baited trees attacked by mountain pine beetle. Here's the distance, 1, 4, and 8 kilometers. These are the formations, triangle, square, and a rectangle. And this is the proportion of the baited trees attacked, 0 to 1, basically. When you look at it, thank you. When you look at it, you see no difference. Absolutely no difference in terms of distance or in terms of formations. Beetle attacks pretty much uniformly on the landscape. That was really, really surprising because traditionally we suspect that if the attack that the bait density increases, perhaps attacks will congregate, but that's not the case. That was a surprising news for us. And then if you look at the same thing, the number of mountain pine beetle attacks on each baited tree, these are the beetle attack densities, the distance 1, 4, and 8 kilometers. Now we can start seeing some differences. In this case, in overall, when you look at it, actually, the square formations, especially at this 8 distance, is really, really pretty doing good job. Same as this triangle formation at the 8 kilometer distance. It's really, really surprising. In rectangle, these are ones that have 6 baits. They did the poorest among all others. Putting too many baits on the same area, it doesn't work. This concept was worked out in some moth species, actually, other forest pest species, especially in orchids, that if you put too many baits, that confuses insects where the source is. They cannot really find where the sources of the pheromones are. In this case, it really proves the same concept. And we also look at overall proportion of the baited trees that mass attacked. Remember, these are receiving 30.25 attacks per square meter and more. This is the data we have. Triangle, square, and rectangle. Again, the rectangle did really the poorest job. Triangle and square is really compatible, especially I'm looking at this 8 kilometer distance. Pretty much there is no difference. The means are pretty much identical between these two formations. These are the number of unbaited trees. This is the spillover attack. We found it, again, triangle, square. The number of attackers neighbors per baited tree. Remember, we have 3, 4, and 6. This is the ratio. This is the numbers. In this case, again, ignore that. In the square formation, the 4 kilometers cut a lot of unbaited trees, so this is the one that we should definitely stay away. And here, this is the really important triangle and square formation, we have a limited number of unbaited attack trees in this category. And rectangle is 8 kilometers in capacity. The number of beetle attacks, remember, this is the proportion, number of beetle attacked by a mountain biker. This is the number of mountain biker attacks on each unbaited tree. This is the one that really one of the most significant results we have, suggesting that at this square formation, at 8 kilometer distance, we have very few trees that attacked. Attack densities are high. Right. This is the lowest, basically, the lowest attack density here. Triangle was my favorite so far, but after these results is definitely not, because we really don't want to have the bait that creating a lot of spillover attacks around it, especially when the attack density is pretty high in this case. Now, this is my very, very brief conclusions. First of all, numbers and the proportions of mass attack baited trees were similar between square and triangle formation. The square formation had the lower numbers and the proportions of low attack trees than the triangle formation, and especially the square formation at 8 kilometer distance basically had the least spillover attack. Because we really, really want to focus, bring the beetles in a very highly concentrated area. We don't want the beetles attack on other neighboring trees. Based on this data, actually, we suggest that this square formation with 8 kilometer distance is the best option we have on the landscape to monitor these the beetle populations in endemic areas. That is the things that exactly we're going to do in 2016. Using this square formation, we're going to test with the different things, the distances 8, 12, and 16 kilometers. I'm really looking forward to this result. It's going to be really, really interesting on the landscape. Now we've been talking with Shane Sadaway from Blue Ridge Company and Ken Anderson from Miller Western. Probably we're going to set it up these new baits in those their harvest plan in 2016 and 17. That's going to be a lot safer because we had some trouble with it to get rid of so many attack trees in 2015. This is the last phase, so hopefully we will be presenting these results next year. So what it means, this is the time that I would like to spend some time. What we found that actually there is really evidence that size of the area is not the only factor that driving this beetle colonization. There are some other factors that could be equally important. What they are the one that's the sort of we focus on. We're going to focus. We thought this is the results analysis. Analyzing these results is going to be straightforward, but this turnout is not, because we become really a little bit more greedy, and then we want to really get the most out from this data. Now we're using the Brooks mortality data. We're going to incorporate here some of these ideas that I put here. First of all, how the beetles behave on the landscape dynamics is really coming to this distance to the nearest invasion front versus distance nearest invasion core. Where the beetles are gathered, concentrated in one area, where the beetles are the nearest invasion front, and how they're putting a baits attack, suitable hosts. When you put the pheromones on the trees, you're suggesting that this is available for you to come and get it. This is creating a sort of under conversion of the landscape. Hopefully we will identify this issue using that Brooks data. And then competition and facilitation. This is the idea that we've been working on for a while. Actually, there might be some competition or facilitation that the beetles at the local area versus the beetle in the long distance. When you put the baits, who's coming? The local beetles are coming or the beetles from the long distance are coming? And whether they facilitate or they'll compete one another. Hopefully we're going to tease out this issue using our own data. If the local, that's the what if, right? If the local beetles initiate attack first, well, this may facilitate colonization of trees by local or distant sources. But if the trees are the trees are attacked by the beetles from long distances, that might have a different effect on the local beetle populations as well as the long distance beetle populations. The size of the local beetle populations in each baited area and how fast they colonize, respond to the available resources, is going to be determined using this data set. Of course, the distance between colonized patches, red attack trees or green attack trees, and where the beetles go from there, is going to be really, really important. Immigration rate of the beetles. I think this is a very tough issue to deal with, but we have a really good chance using this data. We will answer some of these immigration dispersal issues and the competition or facilitation among the local versus long distance beetles. And I would like to acknowledge here our research and EAF, and Saskatchewan Ministry of Environment, and synergies and chemicals that we had help from them in terms of getting the chemicals. We have a Caroline Whitehouse, Calvin Briggs, Amina Hofstadter, Mike Undershoot, and Sanders, and Jen McCormick that from EAF that help a lot. And we feel that a lot of normal people in my life. Thank you.